while we're waiting for the textbook to load, I'll go ahead and show you. Oh, you can just barely see him over the desk. You cannot. Oh, you can barely see the cat as well. Excellent. Oh, there goes the cat. I was hoping they were going to. Oh, there's the textbook. All right. So we go to chapter 1, go all the way to the end. And let's get ready to do the end O chapter problems. Let's hope we can get through these in less than an hour and a half, because after I do the end of chapter problems, I intend to do, okay, good, chapter 2, but I'm going to eat, some dinner first. So let's, darn it. All right, come on. Stay put. Okay. All right, so chapter 1. Structure, stability of atoms. All right, so this is just basic stuff. Protons, neutrons, electrons. Oh my. Oh mio, oh mio, oh Cleveland, Ohio. Okay, so problem 20. Problem 20. Where on the following outline of the periodic table are the indicated elements or groups of elements? Okay. Okay, so this is the problem we're looking at right here. This is a very popular sort of question, because it works really, really well with a multiple choice format. They'll take a periodic table, they might label it, A, B, C, D, E, F, and then ask you where you'll find this sort of thing. So, problem 20. Indicate on the periodic table where you find the element or group of elements. Okay, so instead of trying to draw on my screen, I'm going to actually, no, I'm not going to mess around with that. I'm just going real quick. All right. Boom, 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 boom. All right. So where would we find the alkali metals? That's A. Okay. The alkali metals are the very first column on the periodic table. Okay. Then they also ask about the alkaline earth metals. That's C. That's the second column on the periodic table. They have very similar properties to each other, but distinct. They're called alkali. This might help some of you remember. Alkali or alkaline comes to us from Arabic. This right here, this part right here, the kali, it means potash or potassium hydroxide, a strong base. You burn wood, you collect the ashes, and then you run water through them. You'll get a very, very strongly basic solution, mostly due to this guy right here. So that is where we get our word alkali or alkaline, which means basic as opposed to acidic. That Kali right there is also what gives us the symbol K for potassium. All right, so next up, the halogens. That's B. The halogens are over at the far end of the periodic table. Not quite all the way over. They're the second to last column, the halogens, topped off with fluorine. Then D is the transition metals. This entire block right here is the transition metals. Hydrogen, I technically left off a block, is this guy right here. He's on the top of the far left-hand column, although some periodic tables put him there and simultaneously above the halogens. Because hydrogen's weird. He's the first element on the periodic table. He can show up in both places. And then finally, helium. He is the top of the noble gases. So called because they don't mix with the riffraff. All right. And we bring up this. No questions, looks like. I'm going to be checking periodically, no pun intended, on the YouTube chat. To see if you guys have any questions, if you want me to go over anything again. It looks like there are none at the moment. So next problem is, okay, so 22 and 24. Let's, oop. Okay. Is the red element on the following periodic table likely to be a gas, liquid, or solid? Okay. The red element right here, all the way over on the far right, whether it's going to be a gas, liquid, or solid should be very easily figured out based on the name of the group it's in. The noble gases. It's going to be a gas. In fact, that is argon. What is the atomic number of the blue element? Okay. What are you doing over there? Oh, dog's licking his butthole. All right, the blue element, transition metal, 1, 2, 3, 4 in the second column there. So that is molybdenum, element number 42. Oh, you can't see it because of the molybdenum, element number 42. And next up, name at least one other element that is chemically similar to the green element. Well, they're asking for another element in this group. Okay, that looks like radium. No, radium's right here. This would be one above francium. That's cesium. So we have we're spoiled for choice. We got lithium, we got sodium, potassium, cesium, francium, maybe radium? I don't know. But, well, rubidium, yeah, cesium, francium. All right. How many columns were there on that periodic groups? 1, 2, 3, 4, 5, 6, 7. Okay, so that was cesium. This is rubidium. Potassium, sodium, lithium. Yeah, there we go. I know the periodic table quite well. All right, next up is there's problem 24. We can go ahead and close that. All right, problem 24. If the yellow spheres represent sulfur atoms and the red spheres represent oxygen atoms, which of the following shows a collection of sulfur dioxide units? Okay. In other words, it has to have 1 sulfur and 2 oxygens on each molecule. So 1 yellow and 2 red means that it is A. Oop. This is OS2, this is SO3, and this is a collection of sulfur atoms and oxygen molecules. After 24, I believe, was 28. Yes, indeedio. In the following drawings, red spheres represent protons and blue spheres represent neutrons. Which of the following represents different isotopes of the same element and which represents a different element altogether? So, red spheres being protons, in order for them to be the same element, they need to have the same number of protons, therefore the same number of red spheres. That would be B and C. 2 protons, 2 neutrons, 3 neutrons. So that means these represent different isotopes of helium. This right here is an isotope of hydrogen. Specifically, it is tritium, 1 proton and 2 neutrons. (32). Next page. How many groups are there in the periodic table, and how are they labeled? Okay, the number of groups is relatively easy. That's just how many columns there are, which means there's 18 plus 14 is 32 total groups. How are they labeled? I don't know quite what they mean by that. How are they labeled? I mean, some of them have names, if that's what they mean. Are the red questions the ones that are answered in the back of the book? Let's see. Let's see if they are answered in the back of the book, because I have no idea what they mean by how are they labeled. 18 groups. Well, okay, that's not true. Oh, okay, they're talking about how the names are labeled. Okay. Or, not, whatever. All right, so go back to, oops, that. All right. All right, so they only care about the 18 primary columns, or the 18 columns of the main periodic table. They don't care about the 14 columns down here, which I think is kind of biased and bigoted, but I also think that the F block down here, they deserve it, because they're a bunch of perverts and degenerates, and we don't like them, except when it comes to nuclear bombs or nuclear power. Okay, so how are they labeled? Well, they're labeled 1 through 18. Older periodic tables will label them 1A, 2A, 3A, 4A, 5A, 6A, 7A, 8A for the main group elements, and then 3B, 4B, 5B, 6B, 7B, 8B, 9B, 10B, 1B, 2B for the transition metals, or the transition elements, or group B elements. So that's what they meant by how are they labeled. There we go. Next problem, I believe, was 36. Yes. No, 32 is followed by 34, then 36. Where in the periodic table are the main group elements found? Where are the transition metals found? Okay. Main group, there's the two columns, the tall columns on the far on either end, and then the transition elements or the transition metals are here in the middle. What is a semimetal, and where in the periodic table are semimetals found? The semimetals are the staircase in between the metals and the nonmetals. So metals are on the left, nonmetals are on the right. The semimetals are on the staircase in between them. So every element touching the staircase, running down, whoops, that's not what I meant. Running down the left side of the periodic table there, or running from starting on the left side of boron, is anything's touching that line is a semimetal. In fact, let's see if I can't find an illustration of that. Nope. Wow, these guys are getting really stingy with their staircases. Okay, well, there's the metalloids or semimetals. So basically, everything but aluminum and polonium on that staircase is a semimetal or metalloid. That was 36. 38. Without looking at the periodic table, list as many alkali metals as you can. Well, that's easy for me, but, you guys, fortunately, you had to memorize them, so there's that. You should have already, not necessarily memorized them, but be able to put name to symbol, symbol to name. That's not quite the same thing, but lithium, sodium, potassium, rubidium, cesium, and francium are the alkali metals. And just FYI, my cat judges you. All right. So who is next after 38? 40, 42. Looking at the periodic table, list as many halogens as you can. Okay, they're on the far right-hand side. That is fluorine, chlorine, bromine, and iodine. Those are the four common ones. After that, they start to get highly radioactive, and we just don't work with them. So astatine, and then, they named them. Oh, this has all the names. Awesome. So tennessine. Oh, Tennessee doesn't deserve an element. You okay back there, buddy? You wonder who I'm talking to, or do you just really need to pee? I will rush through these problems and take you for a walk, buddy. Okay. 42. At room temperature, a certain element is found to be shiny, silver-colored solid that is a poor conductor of electricity. When a sample of the element is hit with a hammer, it shatters. Is it likely to be a metal, a non-metal, or a semi-metal? All right. Well, oh no, that's problem 43. 42. It's soft, silver-colored solid that reacts violently with water and is a good conductor of electricity. Is it likely to be a metal, a non-metal, or a semi-metal? All right. Silver-colored solid. that is a big hint that it is not a nonmetal. Nonmetals are dull. They are not shiny. Okay, metals are shiny. So this, but the semi-metals lie somewhere in between. Semi-metals can be, shiny or dull. Okay, you need to not be on the microphone, bud. All right. It reacts violently with water. That is an indicator that it is more likely to be a metal. Metals react with water. If it reacts violently with water, it's going to be on the left-hand side of the periodic table. Is a good conductor of electricity. Good conductor of electricity means it is very much a metal. And here comes the kitty cat to try and steal a pen so that he can bat it around on the floor, get bored, and then the dog will chew it to shreds and ruin the carpet. Nope. All right. So this is a metal. A good conductor of electricity makes it a metal. Non-metals are very bad conductors. Semi-metals are only semiconductors, so they're not great. So this next one, might as well do that. I started it. Room temperature, a certain element is found to be shiny, silver-colored solid that is a poor conductor of electricity. You hit it with a hammer and it shatters. Okay. Shiny silver color, again, means that it is not going to be a non-metal. But it's a poor conductor of electricity. And when you hit it with a hammer, it shatters. Metals don't shatter when you hit them with hammers. They dent or they bend. So this is a semi-metal. All right, 42. This is followed by 44, I think. Nope, 46. What are the symbols for the following elements? Gadolinium is GD. Germanium is GE. Technetium is TC. And arsenic is AS. Just to confirm that, gadolinium should be down here. Yep. Then germanium is up here. Then technetium is over here somewhere. There it is, 43. And then arsenic. Oh, you couldn't see part of that. Technetium's right over here, element 43. Here's gadolinium. Here's germanium. Here is arsenic. Stop trying to steal my markers. God, I need those, and the dog will destroy them. All right, so that was 46, I believe. Yes, comes after 46, but 48, then 50. This is Chem 110. Justice. Chemistry 110. Going through the end of chapter problems for chapter 1 in the Pearson textbook. Specifically for Tri-County Tech in South Carolina. All right. 48. Give the names corresponding to the following symbols. Te is tellurium. Te is over here, tellurium. Re should be rhenium. Where's Re? There it is, rhenium. Named after your kidneys for some reason. Be is beryllium. Right up here. Okay. It's right up here at the top of the periodic table. Yes, I know you really want those markers, but I'm going to put them where I don't think you can get them. There. Here's beryllium. Ar is argon over here. Pu is plutonium. Where is it? There you are, right after neptunium. Plutonium, an artificial element. Then Sb is stibium or astatine. Where you at? And sorry, antimony. Astatine's down here. Antimony. Okay, after 48 comes 50. What is wrong with each of the following statements? The symbol for 10 is not Ti. Ti is titanium. 10 is Sn. Symbol for manganese is not Mg. Mg is magnesium. Manganese is Mn. Potassium is K. Po is polonium, named for the nation of Poland in honor of Marie Curie. The symbol for helium is He, but it's a lowercase e, not a capital E. Okay. 52 and 54 coming next. How does Dalton's atomic theory account for the law of mass conservation and the law of definite proportions? How does it law of mass conservation? That's an interesting question. I mean, the law of definite proportions is part of Dalton's atomic theory. It says that atoms of different elements can combine in whole number ratios to give new compounds with different properties. And it's called definite proportions because those ratios are always the same for those particular compounds. The law of mass conservation. Well, the law of mass conservation states that matter is neither created nor destroyed. So I guess it counts for conservation in that the elements don't just go anywhere when they react, they become part of compounds. Or they separate from a compound that was previously existent and the compound decomposes, or the compounds rearrange the atoms. But the atoms don't just go anywhere, they stick around. All right, 54. A sample of mercury with a mass of 114 grams combined with 12.8 grams of oxygen, and the resulting reaction gave 123.1 grams of mercury oxide. How much oxygen was left over after the reaction was complete? Well, I'm guessing that we're supposed to assume that all of the mercury got used up in this reaction. Okay. So all the mercury got used up, and we're left with, just oxygen after that. So it should have been 114.0 plus 12.8. We had a total mass of 126.8 grams, but we only formed 123.1 of the mercury oxide. Okay. So anything left over, assuming we used all of the mercury, would have to be oxygen, and therefore you're going to be left with 3.7 grams of oxygen. (60, 62, 64). If the atomic weight of an element is X, what is the mass in grams of 6.02 times 10 to the 23rd atoms of the element? Well, that would be X grams. Because 6.02 times 10 to the 23rd is Avogadro's number. As always, I want you to keep in mind, this is not going to be on the formula sheet. Avogadro's number is not one of the numbers they're going to give you. You're just going to have to remember that. Okay, that's why I'm stressing it. 62. If the atomic weight of an element is X, what is the mass in grams of 3.17 times 10 to the 20th atoms of the element? Ooh, that one's slightly more complicated. That one we're going to have to do a little bit more math. Okay. So basically, they're asking what fraction of a mole is it? 3.17 times 10 to the 20th divided by 6.02 times 10 to the 23rd. Bring up the handy dandy calculator. Eventually. Okay. Giving us a really, really small fraction, 5.27 times 10 to the negative fourth. What that means is that this fraction here is the fraction of X. So if 1 mole basically would be X grams, then 3.17 times 10 to the 20th atoms is only 5.27 times 10 to the negative 4th times X grams. So a very small fraction of the atomic mass. All right, 62. Next up is 64. A compound of zinc and sulfur is 67.1% zinc by mass. What is the ratio of zinc and sulfur atoms in the compound? Ooh, that is an interesting problem, because we haven't really covered a good way to solve that yet. Ooh, that is a good brain twister they gave you there. All right, so 67.1% zinc, which means that it's going to be 32.9% sulfur. What is a good way to solve this that you guys would know how to do? Well, let's just dive right in. They kind of made that easy. Because you look on the periodic table, what do you see? Oh, that guy's yellow. Zinc is molar mass of 65.38 grams per mole, and sulfur is 32.06 grams per mole, which means that this bad boy is going to be a 1-to-1 ratio of zinc to sulfur. You don't really have to do much math beyond that. You see that their percentages correspond roughly to their molar masses. Whew, we neatly sidestepped the problem of doing some annoying math there. Huzzah! Huzzah! Cheers all around. 68. What is the difference between an atom's atomic number and its mass number? The atomic number is the number of protons that it has. The mass number is the total number of protons and neutrons. So every atom of an element has the same atomic number, but different isotopes of that element will have different mass numbers. Oh, you can't see what I'm... But atomic number is number of protons, mass number is protons plus neutrons. Okay. 70. The subscript giving the atomic number of an atom is often left off when writing an isotope symbol. For example, C613 is often simply written as C13. Why is this allowable? Because the atomic number is identical with the name of the element. Every atom of an element is going to have the same number of protons. So just identifying it as carbon is sufficient. You don't need to identify it as carbon with 6 protons. That's redundant. All right, 72, 74, 76, 78, 80, 82, 84, 86. Wow, we're just going through every single even problem up to 86. All right. Copper has 2 naturally occurring isotopes, including copper-65. Look at the periodic table and tell whether the second isotope is 63 or 66. Okay. 65. If you average 65 with some amount of 66, then the mass would be above 65. But if you're mixing it with copper-63, then the mass would be below 65. 5 plus 7 divided by 2 is 6. The average goes up from 5. 5 plus 4 divided by 2 is 4.5. The average went down. So, is the average higher or lower than 65? If it's higher, then the other isotope is 66. If it's lower, then the isotope is 63. We look at copper. We see the average is 63.546. The other isotope is copper-63, and there is a lot more of copper-63 than there is of copper-65. All right, 74. Give the names and symbols for the following elements. An element with atomic number 6 is going to be carbon. An element with 18 protons in its nucleus is going to be chlorine, I think. No, one more than chlorine. Yeah, it's going to be argon. An element with 23 electrons. Ooh, that is tricky because there could be several different things with 23 electrons. But let's go ahead. Element 23, the neutral vanadium, would be the most likely one to have 23 electrons because it starts with 23 electrons. Manganese at 2 plus could be a candidate because it could have lost those 2 electrons. So manganese 2 plus would be another possibility. Iron 3 plus would also have 23 electrons. Okay? So that's why they're being slightly tricky, but I think that they were expecting vanadium. Write symbols for the following isotopes. Radon 220. Okay, well, this is a slightly boring problem, but all right. Radon 220 is going to be Rn220. Polonium 210 is going to be Po210. Gold 197. Remember, gold is a U. Silver is Ag. As in, aw, you got me gold. Or, you got me silver, you cheap bastard. All right, so Au 197. '78. How many protons, neutrons, and electrons are in each of the following atoms? Okay. Slightly more interesting problem. So first up we have an atom of nitrogen. Atomic number 7 and mass number 15. Protons, neutrons, and electrons. Okay, to make it slightly more boring, they did not give a charge on any of these 4. If there was a charge, then we'd have to do a little bit of math to find out how many electrons have been gained or lost from the neutral atom. As it is, because these atoms are all neutral, they're going to have the same number of protons as electrons. Okay. After nitrogen, we have cobalt. Lowercase o. 2760. Then we have iodine 131 and cerium 58,142. Okay. So we need number of protons, number of neutrons, and the number of electrons for each of these guys. Now, the protons and the electrons will be really straightforward, really easy, because it is the number on the lower left. The number on the lower left is the atomic number, number of protons, and because these are all neutral atoms, they all have exactly the same number of protons and electrons. So, 7 and 7, 27, 27, 53, 53, 58, 58. All right. That was easy and kind of boring. Now, a little bit more complicated is the number of neutrons. So this is the number of protons by itself. The number in the upper left is the mass number, the number of protons plus the number of neutrons. So to get the number of neutrons, it's this one minus this one. Okay. So for the nitrogen, 15 minus 7 is 8. So we have 8 neutrons there. For cobalt, 60 minus 27 is 33. For the iodine, 131 minus 53 is 78. And for cerium, 142 minus 58 is going to be 84. It is absolutely normal for larger atoms to have increasing numbers of neutrons. As the elements get bigger, you need more and more and more neutrons to keep the protons from exploding, basically. So the smaller elements will have roughly even numbers of protons and neutrons, but the heavier elements, you have to pack more and more of that glue in there. All right, problem 80. Identify the following elements. Okay. This is the problem we're looking at here. In each case, they've given us more information than we need. They gave us both the atomic number and the mass number. We do not need the mass number, the number in the upper left. All we need is the atomic number, the lower left. Okay. So element 12 is going to be, boom, you can't see it because I'm covering it up. It is right here, it's magnesium. And then the next one is element 28. Boop, 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 nickel. And then we have 46 is palladium, right below nickel. And then we have element 74, tungsten. Or, as they call it in Europe, Wolfram, named for a German, I think, whose name was Wolfram, or Wolfram. All right, 82. Which of the following isotope symbols cannot be correct? They're all entirely possible except for this one right here, the bromine. It has a mass number lower than its atomic number. That's just not possible. You can't have -2 neutrons. Does not. Well, could you? Yeah, there's almost certainly such a thing as an anti-neutron, but not in this class. No anti-neutrons for you, no antimatter for any of you until you finish your chemistry courses. All right. 84. Naturally occurring boron consists of two isotopes, boron 10 at 19.9% and boron 11 at 80.1%. What is the atomic weight of boron? Check your answer by looking at the periodic table. Okay, this is definitely, absolutely the precise kind of problem that they would very likely give you on the test. All right. Oh, I haven't checked this in a minute. Nope, no more questions. All right. Okay, so it is 19.9% is 10.0129, and then 80.1% at, where am I looking? 11.00931. Multiply, add, divide by 100 to get our answer. Okay. So it's going to be much closer to the 11.00931 than it is to the 10.0129. Just because there's more of the 11. So 19.9 times 10.0129 plus, let's go ahead and put in parentheses, 80.1 times 11.00931, close parentheses, enter, and then divide by 100 to give us our average of 10.8. When it comes to the sig figs, they really screwed us with those percentages. Only 3 sig figs in our answer. And then we look at the periodic table, and boron is 10.81. Ha ha. I am good at arithmetic. Finally, 86. Magnesium has 3 naturally occurring isotopes. 24, 25, and... interesting, okay. And a third one with 11.01%. Look up the atomic weight of magnesium, then calculate the mass of the third isotope. Oh, good. Absolutely not. This is a lovely little problem. Okay, so the 3 isotopes, we have 23.985 times 78.99. Then our second isotope is 24.986 with 10%. And our third isotope is a question mark times 11.01%. Okay. So you add all those together, divide by 100, and it gives us the average atomic mass of magnesium, which according to our periodic table is 24.305. All right, so now we just do our arithmetic to solve for our question mark. So let's replace that question mark with capital M for mass. All right. So multiply both sides by 100, and then I will go ahead and at the same time carry out these two multiplications. Just to try and save a bit of paper and writing because I'm not made of pens. So 23.985 times 78.99. 1894.6 plus 24.986 times 10. Oh, well. 249.86 plus 11.01 m is equal to 2430.5. Subtract both of these, we're going to get 11.01 m is equal to 2430.5 minus 1894.6, and then subtract 249.86, gets us 286.0. Divide both sides by 11.01. Gives us 25.98, which means, barring a rounding error, we're looking at magnesium 26. Well, no, I mean, that is a bounding. I mean, the mass of magnesium 26 is going to be slightly less, so that is not a rounding error. It's 25.98-ish. All right, what comes next? What comes next? What comes next? 102, 106, 110. We are in the home stretch. Might finish this in less than an hour. All right, so 102. Germanium has 5 naturally occurring isotopes. What is the atomic weight of germanium? All right, so it gives the abundance and the mass of each. Okay, this is a very straightforward multiplication, addition, and then division problem. So I'm not even going to write it down. I'm just going to plug all of those numbers into the calculator. All right, so 0.205 times 69.92, oops, 0.924 plus 0.274 times 71.922 plus 0.078 times 72.923 plus 0.365 times 73.921 and plus 0.078 again times 75.921, giving us an average atomic mass for germanium of 72.63. Technically, thanks to the sig figs, I don't even know where because it's complicated. Because we do multiplication, then we do addition, then so that means that the sig figs get a little bit wonky. But I'm guessing that we'd have maybe 1 decimal place, possibly 2. All right, 106. Identify the following atoms. A halogen with 53 electrons, that's going to be the iodine. Iodine in its native state. Boom. Neutral iodine. A noble gas with A equals 84. I believe that would be xenon. No, it's... Wait, what? Noble gas with... Oh, A is the atomic mass. Excuse me. Or sorry, the mass number, not even the atomic mass. Mass number 84. Ooh, that is interesting. Oh, that would be krypton. Yeah. Oh, neat. As you can see, the average mass is about 83.798. So mass number is close to 84. So that would be krypton. Neat. That was a good twist. That was a good twist. Be on the watch for something like that. They almost got me there. All right, and finally, 110. The molecular weight of a compound is the sum of the atomic weights of all the atoms. What is the molecular weight of acetaminophen, the active ingredient in Tylenol? C8H9NO2. All right. This again, fairly straightforward sort of arithmetic problem. We have 8 carbons, so 8 times, we go up over to the periodic table, 12.011. 12.011. Then we have 9 hydrogens, 9 times, boom, boom, 1.008. And then we have 1 nitrogen, 1 times 14.007. And then we should have 2 oxygens. Yes, 2 oxygens, so 2 times 15.999. So we're going to have to do a scotch of multiplication. 88096 9.072 14.007 31.998. And now we just add those together. 10 plus 15, 17 plus 9, 16 plus 5, 12, 151.165 grams per mole. And with that, we have finished the suggested end of chapter problems for chapter 1. So what I'm going to do is I'm going to take Dog for a walk. I'm going to eat some dinner and wet my throat. I will be back at, call it 8 o'clock to do chapter 2. I will see you